Hey folks, my name is Nathan Johnston. Welcome to Lecture 17 of Vector Calculus, which is all about making use of Green's theorem. So remember, in the previous lecture video, we introduced Green's theorem, which was the statement that there's a really nice relationship between certain double integrals and certain vector line integrals. In particular, that under certain conditions, these are really the same thing as one another. Okay, and we went through some sort of introductory example where we saw, yeah, okay, if I compute this vector line integral, then it really does equal this double integral here. So we sort of verified in a special case. But what we're going to do today is we're going to go through three examples to try to illustrate really how useful this theorem is, okay? There are going to be a couple examples where we have a double integral that we want to evaluate. Well, it's going to be easier for us in some of these cases to evaluate a corresponding vector line integral instead. And then our final example is going to flip this around and say, okay, here we've got an ugly vector line integral. Well, by making use of Green's theorem in double integrals, we can actually evaluate it in an easier way as well. So it's useful in both directions. And well, let's get started. Okay, what are the examples here? Okay, and sort of one very, very common special case of Green's theorem that's particularly neat is what happens if you work with this vector field in Green's theorem. Okay, remember, Green's theorem is this relationship between a vector line integral and then a double integral over a certain scalar field that you build out of the vector field. And if this is your vector field, okay, what happens in Green's theorem is, well, you get the double integral of this quantity, which, well, if you compute these partial derivatives, the derivative of the second entry with respect to x, that's a half, minus the derivative of the first entry with respect to y, that's negative a half, but double negative because you're subtracting it, you just end up computing the double integral of the function 1 over the region, which is just the area of that region, right? If you double integrate the function 1, you're just getting the area of the region that you're integrating over. Okay, so if you use this vector line, this vector field in Green's theorem, what you're going to get is exactly the area of the region that you're integrating around. Okay, so let's see an example of how we can make use of this. Let's suppose that we want to compute the area inside of the ellipse x squared divided by a squared plus y squared divided by b squared equals 1, where a and b are just fixed constants. They're fixed ahead of time. Okay, so this is an ellipse. We could compute this area via a double integral. It's a little bit messy, but you could do it. Turns out that it works out dead simple, though, if you use this vector line integral approach, this Green's theorem approach here. Okay, so what you do is you say, okay, I'm going to choose my vector field to be this fancy vector field that we defined up here, this fancy one that ends up getting you the area when you do the vector line integral. Okay, well, to be able to do the vector line integral, we're going to have to parameterize the ellipse. Okay, so what I'm going to do is I'm going to say, okay, well, this looks an awful lot like a circle, right? It's something involving x squared plus something involving y squared equals 1. So to parameterize this, I'm just going to say, okay, well, how about instead of x being cos t, x over a, the thing being squared, that's cos t. And instead of y being sine t, I'm just going to say y over b. That's sine t because that's the thing being squared over here. And then when I do that, okay, well, what is x itself and what is y itself? Just bring the a and the b over to the other side, and you get your parameterization of the ellipse just looks like this. T is going from 0 to 2 pi like usual, just like the exact same as when we parameterize the circle counterclockwise. The only difference is I've got an a on the cos and a b on the sine t. Okay, so that's my parameterization of the sort of counterclockwise walking around the edge of the ellipse. Okay, and then Green's theorem, here's where the magic happens. Okay, so Green's theorem, it says this vector line integral, it equals, well, exactly this double integral up here, and therefore it equals the area of the region I'm integrating around. It equals the area of the ellipse. Okay, so all I do is now I calculate this vector line integral here. Okay, I apply the vector field to the path, to the parameterization. So I'm just plugging a cos t in for x and b sine t in for y, and I get I get this is my f of x of t. Okay, and then over here, that's my derivative of the path. That's the velocity vector. So a cos t becomes negative a sine t. Just take the derivative of them entry-wise, and that's what you get. Okay, you dot product those together. What do you get? Well, negative b over 2 times negative a. Okay, that's ab over 2 here, and I've got a sine times a sine becomes a sine squared. Second entries multiplied together are very, very similar. The only difference is you've got a cos squared. Okay, and now I've got a sine squared plus this cos squared. Oh, that just becomes a 1. I've still got the AB over 2, which I can pull out of that, 1, the sine squared plus cos squared. So now I'm just integrating a constant from 0 to 2 pi. So it's just that constant times 2 pi, In other words, I just get pi times AB as my area of that ellipse, okay, which you may have seen that formula before, but like this is sort of one of the nicest ways that you can derive it, okay? All right, so this works for any region, okay? If you have some weird curvy region, you want to compute its area, well, parameterize its boundary, do the vector line integral around that boundary, you know, with this as the vector field that you're doing the vector line integral of, as long as the boundary and the region that you're computing the area of satisfy the hypotheses of Green's theorem that we talked about last class. Okay, and maybe I should mention, like, this vector field, okay, this particular vector field, negative y over 2, x over 2, I mean, it's special, but it's not unique. There are other vector fields that will do this exact same thing. There are other vector fields that if you do the vector line integral over these other vector fields, you still get the area of the region in the middle, because really all we needed was that the quantity inside of the double integral in Green's theorem equaled 1. Okay, so as long as del f2 by del x minus del f1 by del y equals 1, then you're good. You're going to get the area when you do this vector line integral. So for example, if your vector field was 0x, yeah, that works as well. If your vector field was negative y0, that would work as well, okay? As long as this weird, funny mixture of first partial derivatives equals 1, you're good to go, okay? Alrighty, let's do another example. Let's ramp up a teeny tiny little bit to an example where, okay, we want to compute a double integral, but it's not a double integral of 1. In other words, it's not just an area anymore, but really it's a bona fide volume that we're trying to compute here. Okay, how can we do something like this? How can we use Green's theorem to evaluate a double integral that's given to us? Okay, and the approach is going to be very similar to the previous example. What we're going to do is we're going to parameterize the boundary of the region that we're trying to integrate inside of. Okay, and then we've got to find a suitable choice of vector field as well. And the only trick is you've got to find a vector field with the property that that funny quantity del f2 by del x minus del f1 by del y equals whatever you're computing the double integral of. And so in this particular case, we're going to want to find a vector field with the property that del f2 by del x minus del fy by del y, del f1 by del y equals y, the thing that we're double integrating, okay? And then we'll be able to use Green's theorem, okay? Alrighty, so fine. How do we do that? Well, it turns out like you have a lot of flexibility in how you do this. There are tons of vector fields with this property, okay? I could choose something like this, for example. I could choose my vector field to be negative y squared over 2, 0. And why does that work? Well, because here, when I do del f2 by del x, I'm taking the second entry. Derivative with respect to x is still 0, so it goes away. And then del f1 by del y, well, that's going to be 2y, negative 2y over 2, so the 2's cancel. It's just negative y, subtract double negatives, I just get positive y. Like, really, all I've done here is I said, okay, I'm just going to forget about all the x crap because there are no x's over here. And I'm just going to put the entire, like, I'm just going to take an antiderivative of this and put it here and then flip the sign of it, okay? So I just said, okay, y squared becomes y squared over 2, but flip the sign because I'm subtracting it. There are lots of other choices I could have made. Okay, I could very similarly have said, okay, I'm going to forget about this second term over here, and maybe just in the F2 entry, the second entry in my vector field, maybe I'll put an x antiderivative of this. I'll just put an xy over here and a 0 here. That would work too. Okay, that would be a fine choice of vector field. Okay, sometimes, like maybe you'll make a guess of a vector field and the integration works out really nasty. Okay, maybe just if that happens, try a different choice of vector field. Like it still has to be one that works. It has to be one that gives you this y on the right-hand side, but there are tons of choices. Some of them are going to lead to easier to evaluate integrals than other. And there's not necessarily a great way to see what the best choice is ahead of time. It's just try one, hope that it works. If it doesn't, try a different one. Okay, so anyway, we're going to try this one right here. Okay, the parameterization, the path going around the border is already given to us. Okay, this cycloid here, I'm just told ahead of time that's traced out by the path from negative pi to pi, defined in this way. Okay, the x-coordinate is t plus sine t, the y-coordinate is 1 plus cos t. Okay, now I'm going to apply Green's theorem at this point, which will tell me that, okay, yeah, this double integral, it's a certain vector line integral. I'm going to warn you ahead of time. I'm going to purposely do two things wrong here, okay? I'm doing two things wrong when I'm applying Green's theorem, and I want you to try to figure out what they are as we're going, okay? I'll tell you what they are when we get to the end of this calculation, and they'll be easy fixes, But still, I'm doing two things wrong in Green's theorem by writing down this equality here. Try to think about what they are. But okay, anyway, Green's theorem tells me that double integral of this funny thing here equals vector line integral around the boundary, which is parameterized like this. Okay, so if I want to evaluate this double integral here, all I do is I say, okay, well, here's my vector field. I plug my path into it. Okay, so everywhere I see x becomes t plus sine t. Well, there are no x's. Everywhere I see y becomes 1 plus cos t, so I get negative 1 plus cos t all squared divided by 2. That's where this comes from. This vector here is f of x of t. Okay, and then remember in our vector line integral formula, we've got to dot that with the velocity vector, or x prime. Okay, so I just take my path here, take the derivative of it entry-wise, so this becomes 1 cos t. Okay, so 1 plus cos t, and 1 goes away, becomes 0, cos becomes negative sine. Okay, so that's my velocity vector. I dot that together, and now I've got a scalar function that I'm integrating from negative pi to pi, and oh shoot, this kind of sucks. It's it's some expression cubed. Probably the easiest thing to do there is just actually cube it out. Okay, so do 1 plus cos t times 1 plus cos t times 1 plus cos t, and you get this junk down here. You get 1 plus 3 cos t plus 3 cos squared t plus cos cubed t. And then you say, oh, that's not much better to integrate. I don't want to do that either. And I feel for you. But there's a nice trick that simplifies this at least a little bit. And that is, whenever you have an odd power of sine or cos, like here, I've got an odd power of cos to the power 1. I've got another odd power of cos to the power 3. In those two situations, because I'm integrating over an entire period of the function, right, from negative pi to pi, that's an entire period of the cosine function and of cos cubed, okay? They have the same period 2 pi. Whenever you're doing that, the integral of these two terms is going to be 0, because the amount of time it spends above the x-axis is going to perfectly balance with the amount of time that it spends below the x-axis. The integral of any odd power of sine or cos over a full period is just going to be 0, because the positive contributions to the area are the same as the negative contributions to the area. Okay, so in other words, we can just forget about these two odd powered terms. I'm just left with the 1 plus 3 cos squared t. And then, unfortunately, we do have to muck around with trig identities a little bit here. Remember that cos squared of t is 1/2 1 plus cos 2t, okay? And once you make that substitution, now it's a little bit easier to integrate, right? The 1 just becomes a t. This 1 here also becomes a t, and this becomes a sine 2t divided by 2. Okay, so you end up getting this junk here, and then you just plug in your endpoints, and boom, at the end of the day, you get negative 5 pi over 2. Okay, and I claimed, remember, I said earlier that no, there are two things I did wrong here. So I want to talk about why this is not the right answer. This is the correct value of this vector line integral, okay? That's not a lie. That really is negative 5 pi over 2. But I misapplied Green's theorem. It's not equal to this double integral here. So what are the things I did wrong? And to illustrate what I did wrong, I want to draw a picture. What did we just compute? So the path that we were given, this top curve here, what was called the cycloid, okay, that's shown here, traced in red, okay? And then the region D that we were asked to compute the double integral over is this thing here, okay? And the first thing that we did that was incorrect when applying Green's theorem is that, well, when I follow this path here, remember, in Green's theorem, the way Green's theorem is set up, the region D that you're doing the double integral over, it has to be to the left of you as you walk along the parameterization, as you walk along the curve, okay? So we would have to parameterize it the other way for this double integral calculation to actually be correct. That's not too much of a problem. We can just flip the sign of the vector line integral that we computed, and that will give us sort of the parameterization going in the proper direction then, okay? So just flip that negative 5 pi over 2 to a positive 5 pi over 2, and that fixes that, okay? We're still not done yet, though, because there's another problem, and that is Green's theorem. Remember, you've got to be doing this vector line integral around the entire border, the entire boundary of the region. And what vector line integral did we compute? We computed this one here, the top boundary. We didn't integrate along this bottom boundary, and we've got to do that. Okay, you can't just say, oh, it's a straight line, it doesn't matter. And like, no, you've got to go around the entire boundary of the region for Green's theorem to actually apply. So that's the second and maybe more important thing that we've got to fix here. Okay, so what we're going to do to fix it is we're just going to say, no, this double integral, it's not equal to negative 5 pi over 2, like we said before. It's the negative of that to flip the direction of this top parametrization, and then plus the vector line integral along this bottom curve here, okay, as long as we parameterize it so that d is to the left. So we've got to be walking along this line to the right in this curve C2 here. So this curve C2 has got to be oriented so that I'm walking to the right along it. Okay, so what I'm going to do is I'm going to parameterize this bottom curve here just by t0, right? X coordinate is t, y coordinate is 0, just because I'm everywhere on the x-axis. I'm just going to have t go from negative pi to pi. Okay, and then I plug that into my vector field. I dot it with the velocity vector, which is just the derivative of this, becomes 1, 0. And I just compute all of that. And what's going to happen is when I plug t0 into the vector field, well, I'll scroll back up and remind you of what the vector field is. The vector field is this thing here, and I'm plugging x equals t into it, y equals 0 into it. That goes away, right? I'm plugging y equals 0 into it. It just becomes 0, 0 here. Okay, so this integral, it becomes the integral of 0, 0 dotted with 1, 0. That's just an integral of 0. It's 0, okay? It turns out that the vector line integral along this bottom straight line path, the bottom part of the boundary, it turns out it doesn't contribute anything, but that's a coincidence. We still had to do it. We got lucky that it didn't contribute anything. It still matters. Okay, but anyway, yeah, so the value of that double integral, it ends up being 5 pi over 2, okay? And then we're done. Okay, let's do one more example. And this one's very opposite in flavor to the previous two examples. In the previous two examples, we were given double integrals and we were asked to evaluate them, and it was easier to evaluate them via vector line integrals. This time we're going to flip it around. We're going to be introduced to a horrific vector line integral, and we're going to say, okay, well, wouldn't it be nice if we could use Green's theorem and double integrals to make this a little bit easier? And that's exactly what's going to happen. Okay, so here is my vector field. Okay, so it's xy squared plus x squared. And then the second entry is x squared y plus x minus y to the power of sine y plus 2. And I want to compute the vector line integral of that vector field along the top half of the unit circle oriented counterclockwise. Okay, this is going to be a nightmare. Okay, we do not want to do that because, for example, we're going to have to integrate something like y to the power of sine y plus 2, except even with a path plugged into that, right? Like there's going to be, like, y is some function of t, and I'm going to be plugging that into there and then trying to integrate that. No, like, I don't know how to do that. I don't want to do that. Okay, so let's use Green's theorem. Make our life easier, okay? So we can't use Green's theorem directly because we're only integrating along the top half of the unit circle, okay? And that's not a closed curve. You can only use Green's theorem when you're integrating along a closed curve. So here's the trick. We're just going to close that curve off. We're going to say, okay, this is the vector line integral that I actually care about. Well, how about I use Green's theorem to compute this area in here, and therefore the vector line integral around this entire closed loop here, and then maybe I'll just subtract off this piece down here. Maybe this vector line integral just along the x-axis, that's easier to compute. I can just subtract that off to sort of correct for its presence. Okay, in other words, like this right here is a proper application of Green's theorem. Okay, if I integrate along the curve C that was given to me, this top half of the unit circle, and then also integrate along this bottom curve that I introduced to make it closed, then yeah, I'm going to get this double integral over the region on the inside. So if I just move things around a little bit, right, just move this term here over to the right-hand side by subtracting it, then I'm going to get the vector line integral I care about is this double integral minus a hopefully simpler vector line integral. Okay, so if we can compute both of these, then we'll be done. Okay, so let's try to do that. Let's evaluate this double integral and this vector line integral and see what we get. Okay, so let's start off with this double integral here. Okay, so del f2 by del x. So I go back up to my horrific vector field here and do the x partial derivative of f2, the second entry. Okay, so I get 2xy plus 1. Oh, thank goodness, there's no x's here. That goes away. That becomes 0. So I just get this 2xy plus 1 when I do the x partial derivative of f2. Okay, and then the y partial derivative of f1, well, that's just another 2xy, okay, and then this term goes away because there's no y's there. So I get 2xy plus 1 minus 2xy. Oh, the 2xy's are going to cancel. I'm just going to have a double integral of 1. That's going to be wonderful. That'll be really, really nice. All right, so that's how far I've gotten on my double integral to start. What about this vector line integral over here? Okay, so I need a parameterization of this curve C2. Let's do just what we did in the previous example, right? It's a straight line segment from -1 to +1, t0, right? My x-coordinate's t, my y-coordinate is 0. So this is my path going from -1 to 1, and I need my velocity vector, so I just take the derivative of my path. T becomes 1, 0 becomes 0, and then I'm gonna, plug t0 into my vector field, and then I'll dot it with 1, 0, see what I get. All right, so this double integral, again, this stuff inside here simplifies to 1. Okay, over here on the vector line integral, what happens when I plug t0 into my vector field? So x is t, y is 0. I'm plugging that into my vector field. So x is t, y is 0. Every term with a y is going to go away, right? So I'm just left with a t squared in the first entry, 0, 0, and a t in the second entry. So I just have t squared t. That gets dotted with 1, 0. Things are simplifying down really, really nicely here. Double integral of 1 over the region. Well, what is the region? It's the top half of the unit circle. What is that area? Well, pi over 2, right? Remember, whenever you're double integrating 1 over a region, that's just the area of the region. So it's half the area of the unit circle of radius 1. So it's pi over 2. And then over here, when I dot these together, I just get the t squared. I integrate that from -1 to 1, and I'm going to get 2/3. Okay, so my final answer for this one here is pi over 2 minus 2/3. That's what that horrific vector line integral from the start that I had no hope of evaluating directly, that's what it equals. It equals pi over 2 minus 2/3. All right, and that's all I've got for you today. Thanks for watching, everyone. Next class, we're going to talk about how you can think about Green's theorem, because we still have not really talked about where it comes from. Like, we've talked about how to use it, but where does it come from? How can you think about it intuitively? Why should this weird double integral equal this vector line integral? That's what we'll talk about next class. So we'll see you then for that.